for that. We won't be in the classroom, and it's not something that I can broadcast since it's a tour. So if you can't make it, there is a procedure online, and I'll come up with some sort of supplementary assignment for you if you aren't allowed to be in class, or can't make it to class. But try to review that procedure before we go to the tour, because you'll just understand what they're doing a little bit better. And it's in Moodle under next Monday. Make sense? Okay. All right, let's do attendance. Hayden is here. Joe. I see that. Marcus. Marcus, can you hear me okay? Great. Porter. Okay, Tell, Lynette. Sam. Okay, great. Jack, I saw you were online. Kyle's here. Amber. Great. Jennifer. Great. And Haley, I saw you were online. I just had to do another one of those early warning things for the College of Technology. So I was looking at everyone's like attendances and stuff. And Kyle, I think that sometimes because you log on late, I have you marked absence for things you were there. Yeah, so figure out the ones that you were actually there for, and I'll switch it.
I completely missed like 3 or 4 classes complete.
Yeah.
And they're different ones. That's why I was like, I have bad attendance, but I just figured it would come up, or maybe it wasn't in yet, or I don't know.
No, I think some of them I marked you absent when you just were late.
Right, and I don't know how to go back and fix that, because I don't know which days, other than 2 days ago, at the end of the day, that comps, I think. That one, and then I don't know about the rest that are completely missed. Do you know what I'm saying?
So for all the ones that are on YouTube, it shows the participants in the Zoom. So you should be able to see if you were asking questions or logged on, and be like, hey, you marked me as absent, but look, I'm clearly on Moodle that day, or clearly on the Zoom that day. I was just late.
How do I know which days I'm on?
So if you go in your Moodle and you look at your attendance, it will show you if I marked you absent or present or online or whatever each day. And so the ones that are absent, you can then say, hey, I wasn't actually absent. If you want to. It's also not more than 10%.
It's here. I just didn't know how to go about this.
Yeah, just let me know, because I think that happened. I just don't know which days it happened. And in future, when you get online, make sure I know that you're showing up, and then I change your attendance.
If you go into grades and then go into attendance, and you get the grades. And then it should.
Yeah, because my career is dragged down because of that. I think, one, I didn't get a good grade on the only quiz that we have in the class.
Sure, but the resume and all that stuff is worth way more in that class.
Right, and that's kind of what I was thinking. That's the biggest one. It's at an F, so I just need to go in there and look at it. And I'm pretty positive that was like one other class that I didn't make it to, whether it's, I don't remember if it was election or whatever.
We had a quiz in
The operator types.
And I think there's a couple of them that put me down. These, but also I have a couple quiz
You did that quiz, Joe.
Yes, ma'am.
Does that mean anything? You said there's somebody was checking on it or it's a program, you said?
Yeah, so the College of Technology has this early warning thing, where essentially within like the first 2 weeks of school, and then right after the first exam, and then I think one more time right on midterms, they ask me if I have any students who have low attendance, missing assignments, if I've identified math or reading skill inadequacies for the course in a student, and if you have any low assignment or test grades. And it's kind of hard because like I can mark no concern, but if I have like nothing to base it on in the class, like I have to kind of just leave it all blank. So I know a couple of you got contacted that's like just because maybe the very first quiz in that class, like you were busy the first week back to school, you didn't do great. That doesn't actually mean I'm worried about your performance. I just have to tell them, well, the only grade I have was low, right? This round, I feel like is way more information. So the first round, if you're a freshman and you're not showing up to your classes, it's really useful to know that in the first couple weeks, because then the support staff can like reach out to you and be like, hey, it's not high school. You have to be in class, right? This one I feel like is a lot more useful because now we can see if people are showing up, if they're getting it, if I'm seeing weaknesses where like tutors maybe need to reach out, or if you got much lower grades in classes, knowing that like, hey, these are classes you need to work on, and then they can reach out and make sure you're aware of all the support services to help you with those grades. And though I don't know how much they listen to my comments, because like some people have had a few absences, but they've been communicating with me and like watching the videos, and like, yes, they've had absences and I do have to report that, but I'm not actually concerned. Or yes, we got a low test grade, but all their other assignments are really good and they're studying and they're working with me. Or hey, this person had a really low test grade and they still haven't come talk to me about what's going on. Like, so it's just to let all the support staff in the College of Technology kind of know who to reach out to. That's what it is.
So the YouTube thing and back, how do I tell absence then? Because you didn't start the YouTube thing, right, for a couple of weeks?
Correct. So if there's a class you're marked absent that you're pretty sure you came to, just let me know and I can send you, because I still have the recordings. So I can send you the recording from Zoom, and then you can see if you're on the participants list. So if it's not on the YouTube channel, because yeah, I didn't figure out how to do that. I didn't even know it was an option until a little bit later in the semester. And every now and then I still forget to turn them on. But we are live.
There's quite a
today.
few days that I'm missing. That was my concern. There's gonna be quite a few of those, I think. I mean, I'm not like there 5 minutes early online all the time.
Sure. But I mean, if you have notes in your, if you date your notes, you're gonna be like, well, I know I was here.
I don't even really take notes. It's kind of just scribbles.
Okay. Well, I know some of them are wrong. You're welcome to try and figure out which ones, and I'll change it. Okay, let's start the lecture. We're going to talk about stress, strain, and elasticity in metals. We're going to start with strain. We're going to introduce stress, and we're going to talk about this stress-strain curve and the relationship between the two. And from that curve, we're going to pull out a specific piece of information called Young modulus, which relates to elasticity, which we're going to introduce. We're going to talk about more in another lecture. Then we're going to talk about this tensile testing, which gives us all this information that we will get to see next week. Okay? When a metal, any metal, all metals do this, is subjected to a load, it gets distorted or deformed. This happens always, no matter how strong the metal is, and no matter how light the load, right? So at an atomic level, there is some distortion or deformation that happens under every load. even if the load is just the weight of the metal itself suspended and there's not an external load besides that, this always occurs.
So all metals.
All metals, yes. The intensity or degree of that distortion is known as strain. So metal strain is essentially how much it distorts under a load.
Hey, can you share
Okay?
the PowerPoint on the
When the load
thing?
is small,
Or not?
you're going to get a distortion that probably, if you remove the load, the metal is going to spring back into its original shape. That distortion will disappear when you remove the load. In this case, we call that elastic strain. Think of a piece of elastic. When you stretch it or pull it, and then you let go, it springs back to its original dimensions, right? Same thing happens to a metal. We don't always see it. It happens sometimes at the atomic level. But if the load is so light and so small that when you remove it, the distortion disappears, it's elastic strain. If the load permanently deforms the metal, so if the strain is permanent, it's called plastic strain. And if you think about a brittle plastic jar, you do something like drop a brick on it, put a sudden load on it, it shatters, right? Plastic strain means the deformation is permanent. Strain is measured as the total elongation per unit length of a material. So what it's saying there is you have some sort of applied stress. So imagine a pipe that's attached at that door and that window. It's going all the way across the front of the room. If I sit on it, I'm creating some strain that's causing it to deform. It's going to bow down, right? That means that throughout the whole length of that pipe, it has essentially lengthened, right, in order to create the bowing, right? It didn't go from being this length and straight across to having that bow in the middle without some elongation, right? So we measure the total elongation in inches over the original length in inches, okay? This is a lowercase delta. You guys are used to seeing the big triangle delta for meaning a difference, right? Delta T for two different temperatures. The same concept, except they use the lowercase delta here, okay? And then L is our original length. So from this relationship, essentially you can see that all we're comparing is the new length to the old length, which tells us then how much deformation there is, right? Which goes right back to our definition of strain being our deformation under a load. Does that make sense? So you can kind of see what's physically going on based on this expression mathematically?
So what is the formula, like E, or the E equals?
Yeah, epsilon equals delta over L. And it's in units of inches by inches. Right? So this is inches and this is inches, but you don't cancel those. You make the unit inch by inch. Okay. Stress is the internal resistance of that metal to deformation from strain. So it's the counter force of strain. When I sit on that pipe that's across the front of the room and I try and deform it with my weight in the middle, the metal's resistance to that occurring because of its strong crystal structure is stress, right? Essentially, the load is performing work on the atomic structure of the metal. The metal wants to stay in its very rigid, strong crystal structure with order to the atoms that keep it from deformation, right? That it's not easy to deform. That's why you use metal in high strength applications, but it does happen. So that load is giving its energy to the process of essentially trying to destroy that crystal structure, right? It's trying to force it into a different arrangement. That's our deformation, that's our strain. And since that process takes energy to do, the energy the metal essentially has to put into maintaining its same configuration is the counterforce that we define as stress. Does that make sense? Let's see here. The board is hard to read. Let me share the presentation with you guys. I'm sorry. There you go, Sam. Should make it a little easier. Okay. Stress is impossible to directly measure. We can't directly measure this. So what we do is we say, okay, we have an external load, and we know how much of the pipe area it's applied to. And so we're going to equate stress to the load per unit area, right? Or pounds per square inch, right? The load per unit area. Technically, the technical wording for this is the force applied per cross-sectional area perpendicular to the force. So if I'm sitting on a pipe that's stretched across the front of the room, my force is going in what direction? This way, right? Down with gravity. So you're going to measure the cross-sectional area perpendicular to my load sitting on the pipe, so that across the room. Okay? And it is essentially your applied force in pounds force over your inches squared. Okay? Force over area. Because this is the resistance to the load. So the load is a force acting on an area, right? Based on how much that load and how big that area is, we know that the metal is going to respond in a way related to that size and load. And since we can't measure it, we measure the load put on it. Does that make sense? Everyone online following with that?
Can I ask you a question? So that would be, so the applied force would be like, say, 100 pounds over an area of like a 48-inch pipe?
I mean, I'm not like 48 inches, right? So it'd be where, if we're talking about my example where I'm sitting on a pipe, let's say maybe that I managed to sit on a 12 square inch area, right? It'd be where the load is applied.
Okay, not the full length of the pipe, but just where the load is applied.
Correct.
Okay, thank you.
Yep. Okay, so it should be pretty obvious. Stress and strain are then related, right? One's the force, one's the counterforce. In material science, there's a graph of this relationship called the stress-strain curve. And for every metal, it has essentially this shape, okay? This area here, from 1 to 2, did you guys do in math what linear relationships mean? Do you know the equation for a straight line, for example?
Like that, and like a slope.
It's a slope, right?
Right. And so,
Y equals mx plus b.
exactly. So, the portion of this curve here, and for those of you who are online, the portion of the curve from here at point 1 to here at point 2 is called our elastic region. In this part of the metal elongating under stress because of the strain of a load has a linear relationship. That's where elastic strain occurs. And what was the definition of elastic strain?
When it returns to its original shape.
It returns to original shape. So as long as you are having this much elongation at this level of stress, your metal is going to bounce back essentially to its original form. So the whole range of stress from 1 to 2, you're only going to get elastic deformation.
From 0.1 to 0.2.
Yep, between the little dots marked 1 and 2.
What you call it, elastic deformation?
That is interchangeable with elastic strain.
But you call the region the elastic region.
Yes,
1 to 2 is elastic.
yes, yes, Jill.
0.1 to 0.2, because I've heard 1 to 2. It's got to be 0.1 to 0.2.
So
Is the elastic region.
it's this straight line.
Okay,
And they put these little 1 and this little 2 on the graph.
I'm reading the 0.1 and 0.2 on the bottom, but I guess that's not right.
No, these numbers will be different for every metal. And the numbers over here will be different for every metal. But every metal will have some amount of elastic region. The elastic region is whatever the straight area is. And we're going to talk in a minute about some things we can determine about the metal, which is why I asked you guys if you knew like equation of a line, because mathematically using that, we can tell some things about a metal. Okay? Because here, our ratio of stress and elongation, or essentially strain, right? Because this elongation is deformation. They're just putting it in percent here. But this is essentially telling us about our strain. The ratio of stress to strain here gives us something called Young's modulus. And in your reading, you're going to read about Young's modulus and Hooke's law, which essentially were a couple people who studied metals and their behavior under stress. And it tells us how elastic a metal can be and how likely we are to have a metal return to its original form and be in plastic deformation instead of going forward to, for example, from this point to this second point to this fifth point, this is the plastic region. Everything that happens here is plastic deformation. And someone online, what did plastic deformation mean?
It's permanent distortion.
Permanent, yes. So once you get past this number 2 point and you're out of the elastic and you're in the plastic, your metal is not going to recover. This load has permanently deformed or elongated your metal. Okay? Based on knowing that this is the plastic deformation and this is the elastic, what do you guys think the yield point is?
Point where it changes from elastic to plastic. Yeah.
It's a little bit past the point where it starts to change. You're on the right path. This is where you can start to observe that it's changing. There's this little space where you're no longer in plastic deformation or elastic deformation, but you can't tell without very specific measurements. Here you start being able to observe it pretty readily that you've entered plastic deformation. So for those of you online, looking at the PowerPoint online, right here, this yield point, as you can see, between that number 2 dot and that number 3 dot, there's some continuation of elastic deformation, that straight line, right? And then there's this start right here of this curve where it shows plastic deformation. A little bit of plastic deformation starts to occur before we can observe it. That yield point is the stress at which observable plastic deformation begins. And that initial plastic deformation is called yielding. Yielding is okay. We may have applications where we don't want deformation to be permanent, but yielding, we're not breaking the metal. When we get over here to the fracture point, we've now deformed the metal so much that it breaks. So yielding, it's still plastic deformation. It's not going to recover, but that metal is still bending and stretching and elongating, and we're okay. And then fracture point, we break the metal. Okay? Based on that information, what do you guys think the ultimate tensile strength is?
Diamond.
Diamond, okay.
So is fracture points part of plastic too?
Plastic, yes.
Okay.
Because obviously if we fracture and broke something, it can't go back to its original condition, right?
Right.
Right? What about online? What do you guys think that ultimate tensile strength might be?
Is that pretty much just the point where it's like at its strongest before it begins to fracture?
Essentially, that's a good way of putting it. It's the point where our yielding has not yet caused a significant loss in the metal's ability to exert a counterforce, right? There's still stress going up here, right? That metal is still exerting energy to stay in its crystal structure despite the strain load that's trying to elongate it, right? At that dot 4, this is where that load has finally overcome the counterforce of stress, and you are clearly on the path to destroying the metal.
So well, it'll obviously depend on the metal to find the ultimate tensile strength.
Yes. The numbers here and the numbers here, for those of you online, the numbers down here and on the other axis over here, those will be different for every metal. However, this shape is universal for all metals. Yes, Joe.
I've got a couple questions.
Okay.
Ultimate tensile strength, so that, is that a desirable place to be? Or is it, you know, you're almost there, you're about to go over the cliff, or is that where somebody might want their metal?
So there's just a tiny bit of flattening here. It's kind of hard to see. Existing in that flat region, typically you want a safety factor, right? Another way to say ultimate tensile strength is the maximum intensity of load that metal can carry, right? So we don't typically in the nuclear industry want to exist at our maximums if going over the maximum leads to failure, right? Typically, in most applications where you don't want to be causing the metal to become brittle and worn, you honestly want to stay over here closer to elastic deformation, right? But sometimes we have loads that are just too heavy, right? And we might exist somewhere in this plastic deformation. In general, nuclear industry is going to come back a little bit, if at all possible. Or they're going to add more pieces of metal so that the load is split between several that might then not all come over and fracture, right? We don't want to exist just culturally where we're close to our maximum and anything over the maximum leads to an accident, right? That's why we say, you know, if this was temperature of our melting fuel that's here, we set the reactor limit way back here, right? We do the same thing with our metal loads. Some applications, some industries might have more comfort with being closer to the maximum, especially if it was for not an extended amount of time. Like construction, you might have something where you're supporting something temporarily until you can pour the concrete around it, for example. And that bridge, you might clear people to drive under it while you're doing that construction, right? Because it's not going to be held here forever. So then as the metal contracts and expands, with the temperature changes, and this changes a little bit, you're not worried about starting to head towards your fracture point. Does that make sense?
Yeah.
Okay.
I had another question.
Yeah.
Jack's little problem about 100 pounds on a 48-inch pipe. I believe that comes out to 2.08. If you divide it, is that 2.08 pounds per inch?
Pounds per square inch.
Per square inch. And does that figure take the place of stress? Because stress can't be measured? Is that what you would call stress?
Yes.
Okay.
Yes. Our pounds per square inch will be our stress. Okay. So I mentioned Young's modulus and Hooke's law. In the 1600s, an English scientist named Robert Hooke showed that the elastic range of material, so on this graph, what's our elastic range?
1 to 2.
Yep, our 1 dot to our 2 dot. Because he experimentally showed that its strain is proportional to stress, that's why we know this is a straight relationship, right? The elongation of a test bar is directly proportional to the tensile force and the length of the bar. So our load, our force over our area, okay? So stress and strain, directly proportional, and inversely proportional to the cross-sectional area and the modulus of elasticity. What this means is that he experimentally showed that simple linear relationship between stress and strain is true, okay? Young's modulus, or the modulus of elasticity, this is a constant in a ratio, right? So essentially, when we have this ratio and we relate stress and strain together, and we call this the modulus of elasticity, we know that ratio is going to keep equaling the same thing, because as you go up and down the lines, both stress and strain change the same amount. Okay? So this essentially is the constant of the relationship between stress and strain. And we can put that mathematically. Who remembers what this epsilon means?
It is strain.
Strain. This sigma is stress. And the big E is Young's modulus. Okay? So essentially, our line here can be represented as strain over stress. This whole area, strain over stress, is going to be related, which means if you know it at one point and one other point, you know it for the whole line, right? Because you've got that equation that goes through that whole point. What this is telling us is that this measure of stress over strain, which represents our elastic region, is telling us in a numerical value how resistant the metal is to elastic deformation, right? Somewhere there's an amount of load that doesn't create any deformation, right? If we took the metal leg from these tables in the classroom, stuck that table on its side, and put a feather on it, have we created enough load to create any stress? No, right? That metal has some resistance to deformation. There has to be some minimum amount of load that starts creating stress, right? How resistant that metal is to elastic deformation is going to determine essentially the slope of our curve, right? So our relationship is going to show us how easy it is to deform a certain metal. Does that make sense? Okay. We're going to talk some more about Young's modulus and elasticity because it's very important in the quantity of metal. And we're actually going to we're going to do some calculations so that if you have a metal of a certain size under a certain load in a certain place in your plant, you understand how close it is to its ultimate tensile strength. We're going to go through some of those in class, but here's the first set of the theory. Yes, Joe.
You said that this shows the relationship between what now?
The resistance to elastic deformation.
That's what that equation shows.
Yes. Okay. Tensile testing is used to determine the load carrying ability and amount of deformation before fracture. We use a tensile test to create the stress strain curve. Essentially what you do is you take a little sample of pipe, you anchor it to a rigid support, and then you put a little gripper at one end, and you gradually apply more force straight out, okay, elongating it. And so the sample slowly gets pulled apart, and you watch it elastically deform, and if you released it, it would return. Then you watch it plastically deform, where if you release it, it stays, and then you watch it fracture. And you can take various measurements as discussed in that procedure, and as we'll see in the demonstration on, I believe, Monday, how exactly they measure each part of this stress strain curve, and we'll get to see a metal go through elastic and plastic deformation. I was going to watch this video, but we're a little bit short on time for that. We've only got 5 minutes. So Sam asked, wouldn't they want all metals being used to stay below the yield point? So not all plastic deformation is entirely bad. Some amount of plastic deformation can be tolerated, and it just depends on how much load and for how long you're carrying it. But in general, you don't want to tax your materials and start seeing them deform. So yes, it is a good rule of thumb to say we're going to stay below this yield point. There are some applications where you might go above. In general, like constructing a building, constructing a nuclear power plant, having these materials that are structural in some way, one of the design things that happens in that structural design analysis is it shows why the metal in that certain arrangement is going to stay below the yield point. That's why, for example, a mechanical engineer or some civil engineers might study how a truss essentially distributes a load so that each piece of the truss has less of the load on it than any individual would by itself. So you can stay below that yield point, so you can actually have straight floors in your skyscrapers that don't dip, right? That's why if you go into certain buildings with heavy industrial equipment that might have like potato trucks drive across them, for example, you might see a sign that says maximum load is blah, blah, blah pounds per square inch, right? That's essentially saying our yield point in the structural material that makes up our floor has to stay below this load in order to not exceed that, right? That's where those signs come from. So yes, Sam, that would often be the goal, though not every single application is that necessary. Any other questions? Okay. I do encourage you, if you have the time and you want to hear it said again another way, to watch this little video. They go through these concepts and show you the piece by piece how they put that graph together. It is useful, but we'll also watch it done in our little lab tour.
Do you have a class right now?
The same one. Because I tried to click on it.
You probably have to hit control and click it. Yes, Sam, I can answer your other question. And yes, Kyle, I do have another class after this.
I'm gonna go try and fill through some attendance, but I doubt all of it is gonna get solved.
Yeah, Sam, don't worry about that project right now in thermo. I told you guys I was a little behind on updating the Moodle because we've had to adjust some. That is not due because we haven't even started talking about the first laws yet. So you can keep checking with me to be sure, that's totally fine, but I promise as soon as I have some time, I'll get that page actually updated. I've just been having to create new content because we had to review some stuff and it's taken a lot of my time. So I apologize, but I'll get it. All right, see you guys in components.
Which assignment is Sam talking about?
There's a law